What you are looking at is a slightly simplified version of our mechanical integrator in action. Before we get into why it works, let's first look at how it is operated. The blue time disk rotates at a constant speed. It represents the current t, or time value, of the graph. The rod moves the central wheel. It acts as the machine's input. The rod is constantly moved to match the value of the input graph at that time. Finally, the cylinder is the output. The net rotation of the cylinder at any given time is the integral from 0 to t of the input graph. Here, we see that the integral from 0 to 12 of the function x over 2 sine 2x dx equals about negative 1.39, which we can verify on our calculators. But how is this strange set of meshing wheels able to calculate an integral? To find out, we have to learn a little about how mechanical computers work. In mechanical computers, numerical values are represented by rotation. One of the simplest operations you can perform is multiplication, using gear ratios. If two gears are the same size, then the follower gear rotates at the same speed as the driver gear. This is equivalent to multiplying by 1. However, if the follower is 3 times smaller, then it will rotate 3 times faster than the driver. This is equivalent to multiplying by 3. The core mechanism of the mechanical integrator is an adjustable gear ratio. The large time disk acts as the driver, and the cylinder acts as the follower. The central rod lets you set the factor of multiplication to whatever you want. To see how this relates to integration, imagine the example of an object moving at 4 meters per second for 3 seconds. We can set the rod to position 4 and rotate the time disk 3 times. The net rotation of the cylinder tells us that the final displacement is 12 meters. But what if, instead of velocity being constant, it is constantly varying according to a function of time? The mechanical integrator allows us to continuously change the gear ratio to match the velocity, while still calculating the displacement. The final rotation of the cylinder is equal to the total displacement, which is the same as the integral of the velocity function over that time. Also notice that the graph of the cylinder's rotation is the antiderivative of the velocity function. And there you go! I personally think it's super cool that a machine with so few parts can calculate something as complicated as a definite integral, and I hope now you have a greater understanding of how it functions.